So let's see. Objective. Those guys, how many guys they didn't come last time? Raise your hand. 1, 2, 3, 4. Did you enjoy your national day? Yes. Okay. Now, the objective here, okay, to introduce Galerkin method. We talk about Galerkin residual method. So all the method which we are talking about here will be called numerical method or residual method or weighted methods. One of them is Galerkin method. Do you know why Galerkin method is important? Those who came last time, why Galerkin method is important?
Where you cannot apply energy methods in some fields.
Oh, when you cannot apply energy method
or potential.
Oh, because there are 3 methods, right?
Yeah.
One is direct method, the other one is potential energy method, and the third one is Galerkin method. So this is how to go from a differential equation to a matrix equation. Okay? Can you give me an example where you can use this? Fluid, right? Fluid, right? You can use Galerkin method. There is no potential in fluid. You have to use Galerkin method. You start with differential equation, and how do you transform a differential equation to a matrix equation? What's the matrix equation? Forces equal stiffness times the unknown. That's it. Okay? Very good. So, Galerkin residual and its use. So basically, the Galerkin method is an approximate method. Normally, finite element is approximate method. And it's going to be, I explained it last time, we are going at the end to solve a differential equation with some boundary condition, right? This is all the engineering. All engineering boils down to this. Governing equation, domain, and you want to solve this governing equation in that domain with a prescribed boundary condition, okay? والله انا اي وش ان انا ام ريلاكس لايك يو. تفضل. اكيد انك قريت المايندفولنس وتلخصها لنا صح؟ تحل الواجب. تعرف كيف تحل الواجب تاخرت؟ لان ما طبقت المايندفولنس. If you use mindfulness you will come before everybody. If you use mindfulness. Now when you go home you study the mindfulness.
The next cycle.
So it's late assignment. This is already been given to you, right? Yeah. Okay. So, differential equation, right? We said differential equation to solve the differential equation. I have to repeat what I said, otherwise you will be lost. I know. Right?
Right.
تكرار يعلم الشطار صح؟ Okay, good. d second y dx squared minus 2y plus 7 equal to 0. This is the differential equation. Can you find y as a function of x?
Yeah.
You need boundary condition. How many boundary condition? 2 boundary condition. Because this is second order, right? Then you will find y as a function of x equal maybe x squared minus 3x plus 4. This is the solution. And this one in the range of x between 0 and maybe 20. This y, if you take it inside here, it will satisfy exactly the differential equation. And we call this is an exact solution because it's analytical solution. Okay? In finite element, we are going to use approximate solution. Why? Because we are not going to satisfy this differential equation at all the points. We'll satisfy this differential equation at the nodes. So basically, this differential equation, if the solution from finite element is y bar. So if you use instead of y, you use y bar, which is approximate. This is from finite element, and put it in the differential equation. What would happen? Minus 2y bar plus 7. Is it going to be 0? No, it's not going to be 0 because this is not exact. So how do you minimize this y bar so that it would approach to 0? You take the differential equation or you take the residual. This is called R. Okay, this is called R. When you put the approximate solution in the differential equation, you get residual. You didn't get 0, maybe you get 0.1. Now, how do you minimize 0.1? You take the differential equation with the approximate solution, which we call the residual, and you integrate over the volume. And you want to minimize, see, equal minimum. So that's it. You just take this differential equation, integrate, put dV, and this should be equal what? Minimum over the volume from 0 to V. Now, can we make this minimum to be equal to 0? Like here, can we make it equal to 0? Yes, we can make it equal to 0 by multiplying by W. You see? Weighting function. So this is the secret. The secret here, how do you make the differential equation satisfy, or the solution satisfy the differential equation, is to multiply it by weighted residual. And now when you integrate them over the volume, it's not going to be minimum, it's going to be identically 0. So how do we do that? What are the weighting function? The weighting function, when it comes to Galerkin method, is what? Shape function. W, shape function. If you take R and you multiply it by N, the shape function, and you integrate, you will get Galerkin method, and you will get exactly the stiffness that you are looking for. You see? So if you take R, which is the residual, and you multiply it by W, which is the shape function, and you integrate over the volume, equal to 0. So it says here, using the Galerkin method, we choose the interpolation function in terms of Ni, the shape function. By Galerkin method, we choose Ni are chosen to play the role of the weighting function of W. I understand now. You didn't understand what I'm talking about until you see it real. Okay, so let us do it for the rod truss. Okay, do you know the differential equation for the rod? If you have a rod here and there is a tension here and a tension here, what's the differential equation? Huh? What's the differential equation? The only thing I know that T is constant along the bar. Do you agree? The tension force along the bar is constant. And T is coming from what? From stress. Stress is equal to sigma times the area, right? And stress, I know it's coming from where? From strain. Strain is du dx times E times A. So, what about if I say T equal to constant? What is dt dx? If T is constant, dt dx equal to 0. This is your differential equation. dt dx in the rod is equal to 0. So if this is T, just take the derivative of this and equate it to 0. d dx of all of this, du dx EA equal to 0. That is your differential equation for the rod. See? It's here. Look at the equation. AE du dx. Du dx is strain. Strain times E sigma. Sigma times A tension. dt dx is equal to 0. So, how, this is your differential equation. How do you find the stiffness using Galerkin method? This is what you want. Do you remember the stiffness for the rod using direct method and potential? What is K for the rod? 1 minus 1 plus 1 plus 1 minus 1 minus 1 EA over L. Okay. So that's it. Galerkin method. Take the differential equation, multiply it by the shape function dx, because you don't have volume for the rod length. Already the area, we used it there. See the area here. You can think of A dx as dv, right? A times dx is dv. Okay, if you integrate this, it should be equal to 0. How many equations? This one? 2 equations? Are you sure? This one is a scalar. This one 2 equation. Why? Because you said I equal 1 to 2. So you will use this equation for n1 and you will use this equation for n2. Okay. One thing don't forget this. Always Galerkin method, it will end up with integrating differential equation. And the integration of differential equation, the only way to get a solution is to use integration by parts. Okay. Why we have to integrate by parts? We said this last time. Anybody will tell me? Huh? It will be 0. What is u? U is linear. U is linear. And this is, if you take the derivative of linear, it will be constant. And if you take constant and you take the derivative, it will be 0. You get nothing. The only way it will work is to use. Okay. So what's integration for part? Integration of u dv equal uv minus integration of v du. You remember that? Calculus? Yeah. Is this calculus or what?
Those two.
Okay. Integration by parts. You just integrate it. Okay. U dv. If this is u, then this is du. I forget about my pointer. But if this is u, this is du. And if this is dv, this is v. Okay. What to do next? Tell me. Now you have u, du, dvv. What do you do? Okay. Can you substitute the formula? Come, substitute in the formula. Okay. ليش ما جيت؟ كم؟ Okay. U integration of u dv equal uv minus integration of v. يلا. Equal to what? Equal 0. Equal 0 because remember this u dv is coming from where? Integration of r shape function dx. You see? And this one should be equal to 0. You see, this is how it comes. Okay. Can you substitute? Yeah, let's substitute. I'll come back. Finish that. What did you do? You substitute.
Yeah, it's there.
Okay. That's all. This is what you did. You didn't want to add. Okay. So you have to put the limit here from 0 to L, and this is from 0 to L equal to 0. Okay. Now, this one is two equation. Why? Because you can use I equal to 1 and I equal to 2. Okay. Let's say for I equal to 1. For I equal to 1, this one would be 1. Now, do you think this is scalar? Okay. What is du dx? You remember what is u? Always remember u. U is what? N1 u1 plus N2 u2. So it's the product of N1 N2 dot product u1 u2. So when you take the derivative du dx, you are taking the derivative of the shape function. You see? So it will be partial of d1 n1 dx, dn2 dx, and u1 u2. So we finished from this. Okay, what about this one? This is also du dx, right? Are you sure what you are doing is correct? Is this correct? Let's compare it with this. Do you think this is what he did? What about here? Du dx, then what?
The shape function.
dni, right?
I equal what?
dni dx. You didn't even substitute right. You have u, you have dv, you have v du. You just have to substitute, and then you integrate. When you integrate this for I equal to 1 and I equal to 2, look, when you put, that's it. This is the first equation, okay? This is for N1, okay? Substitute, and finally, you will get this equation here. Look at the equation. After you simplify, what you need to do, you multiply this row by this column, and you integrate, okay? You get this equation. AE divided by L, U1 minus U2 equal F1X. Don't worry, it will be in the homework how to derive it. It's okay. It's okay. Don't worry, okay? You will have it again. You will have it again, okay? This is when you have N2, okay? You have to know it, okay? This is equation number 2. Then what do? You just gather the term. It will be equal, right? F1X, F2X equal to EA11 minus 1 times what? U1, U2, right? Okay. Did we talk about the other residual method? Okay. Now this is a differential equation here. Okay. This is now a differential equation. Yes, it's differential equation because it's du dx. Okay. So now for this rod here, so there is like cantilever and it is loaded with shear horizontal. So it creates what? It creates normal stress. And the normal stress will be the normal force divided by the area. So we made a cut, we choose an element, and we found P as a function of X. Okay? Everybody knows how to find P as a function of X. Yeah. Half of the area of the triangle, or the area of the triangle, it should be equal to the load. Okay. And then after that, I want you to find U. How do you find U? One way to find U is to put the exact P here, and then you integrate it one time. And you put boundary condition, and you will get P as what? As the closed form solution. But if you don't have the closed form solution, then you have to go to approximate method. What is the approximate method? One way is to do this. This is U, which is now approximate method, which is function of C1, C2, C3. They are unknown constant. So now I'm asking you, how can you find C1, C2, C3? So you take this approximate solution. What do? You put it there in the differential equation, and you put P in the differential equation, and you will not get 0, you will get residual. Why? Because you are using approximate solution. Every time you are using approximate solution, you get R. Now, how do you make this residual equals to 0? You multiply by weight, weighting function, which is the shape function, and integrate. Okay, this is one method. Do you have another method? Yes, we have several methods. Let's go one by one. The first method here is called collocation method. We'll come back to Galerkin. Collocation method, what is this method? This method, it seems that you force this to be R equal to 0 at a certain point. How many constant here? C1, C2, C3. You choose 3 points and you force R to be equal to 0 at these 3 points. It may not be equal 0 between the points. This table, this is 1 point, this is 1 point, this is 1 point. It may not be equal R equal to 0 between the 2 points. And it may not equal to 0 at between the 2 points. Why? Because only you satisfy R to be equal to 0 at a certain point. Look at it here. R equal to 0 at x equal to 0. You put it 0. And you got one equation. And then he took R and he put it equal to 0 at 1/3. He substituted x equal to L over 3. This is the second equation. And then he took R and he forced it to be equal to 0 at 2/3 of L. How many equations? 1, 2, 3. Can you solve for x, C1, C2, C3? Yes. Huh? Arbitrary. I choose. You can choose anything. You can put R at L over 2. I choose these. Huh? So is this correct?
Yeah, that's correct.
This is mechanics, internal force. This is C201. You make a cut, how to find an internal force, right? Anyway, you get now 3 equations with 3 constant. Yes, C1 is here, C2 is here, and C3 is here. And when you put the value of E, A, and L, you get this. Take these C's and put them back into the equation, and you get U here. Now, is this U approximate solution or exact? Huh? Exact? They are exact at only 3 points because you force it to be equal to 0. But if you put L equal to L over 16 or L over 20, and if you put XL over 20, it will not be equal to 0. This is why it's called collocation. You collect several methods, several points. Okay? Collocation. So you are not making it. This is good. At least you found C1, C2. Maybe somebody else maybe use different points and he will get another C1, C2, C3. Okay, you understand this?
Yeah. So it will be exact at the point you choose.
At the point you choose.
At that point will be approximate.
Yeah, and if you are lucky, it will be 0 at the other point. Okay. Yeah, if you see they are 0 at the other point, you said you didn't tell me that it will be 0.
No,
if you are lucky, you might have it 0 also. Yes.
It's only 3 points. Or can choose whatever.
I don't know. How many constant? 3 constant. You want to choose 5 points? It's okay. Redundant, right? You have only 3 unknown. So you need only 3 equations. That's all. Okay. And the more points you choose,
It's accurate.
it will be more accurate. But you have to choose more constant. Okay, what is the second method? We finished collocation method. Now he said, I'm not going to use individual point, but I want to minimize the R to make it equal to 0 over a range. You see? In the first third, in the second third, and in the third, right? So I will satisfy here from here to here, 0 to 1, 3, and what? L over 3 to 2 over 3, and then from 2 over 3 to L. Right? So put the R, he put the R, and put 0 to L over 3. Can you do the integration here? Can you do the integration and you put the limits? Can you do the integration? You can, right? So you get how many equations? 3 equations. C1, C2, C3. And then you can solve for C1. This is called subdomain. The whole thing is called domain. First subdomain, second subdomain, third subdomain. Okay, what's the third method? See, he's integrating. He's integrating there, and he's finding this. Least square method. This is the third one. Okay? So least square method, it means you are not going to minimize R, but you are minimizing the square of the residual. So this is why. Instead of having R, you are having R squared. You are minimizing this. Always you are minimizing it with what? With your constant. Because your constant are the unknown. Okay. So the least square method requires the integral over the length of the rod of the error function to be minimized with respect to each of the unknown coefficients, like with C1, with C2, and with C3. This one will generate for you 3 equations. Okay, use chain rule. What is the derivative of R squared with respect to C? It will be 2R, right? 2R, partial of R with respect to C. This is like reciprocal method, matrix, structural analysis, reciprocal method, or something like that. So this is what it is. How do you do it? Is it hard? No. You have R already, function of C1, C2, C3. Multiply this by the derivative and equal to 0 and put the limit. Okay, let's see the 3 equations. Wow, it's here. Look, look, R with C1 is only AE. Look, AE. R with respect to C2 is this, which is this one here. R with respect to C3 is this. And you integrate, that will give you what? 3 equations. Then you can solve for C1, C2, C3. I think I will change the time because this time, by the time you reach to me, you are exhausted, you feel sleepy, right?
Focus on you.
Really?
Really.
Okay, you don't tell me about mindfulness, you have to breathe, right? In mindfulness, you have to breathe. Like that, okay? And you just add it slowly, okay? Not only you take inhale, but when you exhale, you exhale slowly. You control. It's not like this, as if you are sighing. It's not like that. Take inhale, and when you exhale slowly. Do you know what happens when you exhale slowly? It slows down the rate of your heart. Makes it relax. And if you train yourself to do this exhale, slow, you will see your heart rate will be slow down. It means you are relaxing your heart. You are relaxing your heart, it means what? You're so much relaxed, right? Just inhale and exhale. You don't have to pay money. You don't have to purchase it. It's with you every time, right? So this is what happened when I am with my wife. I always inhale and exhale. Okay, and she's surprised how much still I am still laughing, right? I don't tell her the secret. Right? Inhale and exhale. That's it. Try it with your wife. She says, you are changing. Tell her, yeah, I know, I have a technique. Okay, let's go back to this. Now, least square method is easy. You get 3 equations with 3 unknown. C1, C2, C3. Okay, Galerkin method. What do you do with Galerkin method? You know it. You take the R, you multiply by the shape function, integrate, right? That's it. What are the shape function? The shape function, this is the shape, first shape function, second shape function, third shape function. So this is the 3 equations. So you will take the R, you multiply the first equation by x minus R, integrate. You take the R, you multiply it by what? By N2, N3, and you will get 3 equations. N1, N2, N3, integrate, and you will get everything. In conclusion, what is it? Tell me. How many methods? How many methods? 3 or 4 or 2? 4 methods. Collocation method. Subdomain method. What? Least square method? Okay, very good. So that's it. This finished the first presentation.
There's no example.
That's what you'll see. I'll see it in the homework. I said.
There's no question.
Huh?
The last question was Galerkin.
Look at this. You see, it means you didn't know about the homework yet.
I know, but for that I'm asking. It's not.
That's it. So don't worry about it. Just submit it on Tuesday, and that's it. See the trick here? Already I put it there in the homework. And that's why I responded on Tuesday. Because I know I didn't cover it.
It's not because the national day.
What?
It's not because the national day.
National Day? What do you mean by National Day? National Day, you have to work hard. This is how you celebrate your National Day, right? It's to become a good citizen, right? That's all. Very good, very good. Okay, where should I go? You let me forget what am I supposed to do? Just open the other one, right?
Yeah.
Okay, this one?
Yeah, that's it.
Okay, this is very interesting now. Okay,
The beam.
now we go to the beam. That's it. Enough spring, enough truss. Now we go to the beam. Go to the beam. What do we do? What do you think? Now you understand the procedure. The same thing that we did on the spring and we did on the truss, we'll do it for the beam. We have to use direct method. Direct method to get what? The stiffness. Okay. What are the procedure for finite element? There are 8 steps. What is the first step? No. Before discretizing. Select element type. Because it's a beam, you will use long one, right? 1 dimension. You will not use the area and you will not use volume, right? Just like the road. Okay, so this is the type. Then what? What is step number 2? Discretize? No. Displacement function. U, which is equal N1, U1, N2. In fact, before you talk about displacement function, you need to talk about degrees of freedom. This is the element. You have 2 nodes, one here and one here. For the rod, only 1 degree of freedom. It's either tension or compression. For the beam, if you have a beam, and you have node here and node here, how many degrees of freedom for the beam? 4 or 5? Only 2. Only 2, which is deflection and rotation. Right? Yes. So how much? You have 4, right? Yeah, 4. It means the size of your matrix should be 4 by 4. Or no, 2 nodes. 2 nodes, each node has 2. It means 4 by 4. Maybe V1, V1. V2, V2, right? Okay. Okay, good enough. So let us do this. To review basic concept of beam bending. Do you know anything about beam bending? Normal plane remain planes. Remember mechanics. Okay, Euler-Bernoulli equation. Derive the stiffness for the beam. Demonstrate using direct stiffness. And then we'll illustrate some when you consider the shear. Because sometimes in deformation, you consider the shear. Who's good at structure? Who likes structure? You like structure? You don't like structure? You don't like structure, that's a big problem. You like structure, right? What absorbed deformation is either in bending or shear. But for the beam, what dominates is bending. right? No, you can neglect. Do you neglect the shear always? No. Which cases you don't ignore the shear? Concentrated load. Now about geometry of the beam. When you have short, when you have deep beam, which is short, with the ratio of length to the depth, certain value, you cannot neglect the shear. It means you have to include bending deformation and shear deformation. Otherwise, your result is not going to be right. So let us start with the easy thing. The easy thing is we use the only bending. Yes. We derive the stiffness metric for simple beam. A beam is a long, slender structure member generally subjected to transverse loading that produce significant bending effect as opposed to twisting or axial. This bending deformation is measured as a transverse displacement and rotation. These are the degree of freedom, deflection and rotation. Hence, the degree of freedom considered per node are two things: transverse displacement and rotation, as opposed compared to only axial displacement for the bar element. That's it. You can see here, this is a beam element, and you can have, this is node 1, this is node 2, and in node 1, you can have what? You can have displacement and rotation, and there also displacement and rotation. You can have force, and you can have what? Moment, and you can have force and moment. I think now you can construct your stiffness. You have to relate forces to displacement. Okay, can you tell me what should I write? Vector equal to a matrix times a vector. Okay, this is a vector equals a matrix times a vector. What should I write here? F what? F1y. Then what? M1. F2y. M2. And here V1. V1, right? And this one V1. V2. V2. This we want to derive K. What is K? Huh? Yeah, I know how you derive it. This you remember it, right? You will see the formula. You will be happy to see it now. Okay, we will derive it. Okay. How we are going to derive the stiffness? Using direct method. Do you remember the truss? How did we find EA over L 1 minus 1 minus 1? I think we have two figures, if you remember. We have two figures. I think one figure for finite element and one figure for sign convention. I think for the sign convention, we have T here and T here. And then this one, we said what? F1x. And here we said what? F2x. And then we compare this with that. And we said that F1x may be equal to T and what? Minus T, okay. And the other one, F2x equal to T. So exactly the same thing here. We are going to put the forces and we are going to put our sign convention, okay? And we compare the two. Now this is what it's called, beam element with positive nodal displacement, rotation, and forces. Look at this. This is the sign convention in mechanics. Shear is down, moment counterclockwise here. Shear is up, moment clockwise. If you have a beam and you make a cut here and a cut here, what is the shear and moment? Take this element. What is the shear here? Is it down or up? Down. What's the moment? This way. Okay, what about in the left-hand side? Up and that is exactly what you see here. L here is an element. Okay, this one here, L, consider this is the L. Okay, so the shear is down. This is B, this is M, this is shear, and this is M. Now you need to compare it with what? With this one here. What do you think? Shear is what? For node 1, shear is what? Shear is F1y. Okay, very good, because it's in the same direction. Okay, what about the moment? M1 equal minus M, right? Because it's opposite. Okay, what about node 2? Node 2. Shear equal minus, and the moment equal moment, right? Very good. Very good. Okay. So now we need to have a differential equation, right? Okay, do you remember this? I think you remember this, that the shear equal the derivative of the moment and the load equal the derivative of the shear, right?
Yeah.
Using equilibrium, summation of point, summation of moment, using this element here. So in this element here, you're applying summation of y and summation of moment, right? So you get these two equations. The derivative of the shear equal negative of the load, and the derivative of the moment equal shear. Do you remember this equation? EI, second derivative of the deflection equal to the moment. Did you see this? Do you remember this?
Yeah.
Or if you don't like this, EI, Y double equal to M. This is mechanics, right? So that's it. This is what it is. See? It's here. EI times the second derivative equal the moment. Why we are doing all of this? We are doing all of this so that when we find the primary unknown, we can find the secondary unknown. The primary unknown is what? The deflection. What's the secondary unknown? Rotation is secondary unknown, consider. But we will consider phi here is secondary unknown, but we will make it as the fit. Because if this is V1, this is what dV1 dx. If this is V2, this is called what? dV2 dx. Okay, what is your secondary unknown? If you know the deflection and you know, so you can find the shear, you can find the moment. So shear and moment is what? Secondary unknown, okay? This is why. Once you know the deflection, you can find the moment, okay? That's why we need this formula. Okay, so this is our differential equation, mashallah. Fourth derivative, EI. If there is no load, if you have concentrated load, this one will be 0. And if EI is constant, you can put it outside the integration and it would be this one. So this is what? Fourth derivative. So that's it. Your primary unknown is V. Forget about phi. Phi is only the derivative of what? V. So dV dx is phi. Okay, so your primary unknown is V. So your first thing, what is your displacement function? Should it be linear? Should it be cubic or quadratic?
Depends on the load.
Depending on the load, you have to have it in general. Fourth order. Huh. Okay, let's go. Let's go to the, I will give you a hint. For the rod, we have 2 degrees of freedom, right?
Right.
And you have what? Linear. Here you have 4 degrees of freedom. There you have 2 constant to evaluate. You will say U equal A1 plus A2x. And you evaluate A1 and A from the boundary condition. Now you have what? U or V will be function of A1 plus A2 times X plus what? A3 times what? X squared plus
and X cube.
plus A4 times
X cube.
X cubed. Shall I continue?
No.
I stop here.
Yeah.
Means what? How many constant now?
4.
4 constant. Why 4 constant? Because 4 degrees of freedom. Because 4 degrees of freedom. This is the only thing. You have only condition that V equal to V1 at node 1. Right? The derivative of V at node 1 equal to V1. Right? You need what? You need a displacement function with 4 constants. Okay? Let's assume you become genius and say, no, I can work with linear. If you work with linear, where you put the linear? Take the fourth derivative of linear.
0.
0, nothing. You'll get nothing, right? So, steps. Select an element type. Okay? Now, did you see this before? It's in the board, right? It's in the board here. So, this is the sign convention. Always the force up, positive. The deflection is positive up. Same thing here. deflection and force up. Always counterclockwise is positive. Counterclockwise is positive. This is called what? Sign convention, okay? Now, is it sign convention? Sign convention for the shear and moment. This is for only finite element, okay? Now, yeah, you are right. It is cubic. A1x cubed, A2x squared, A3x, and A4. Is this good form to deal with finite element? In finite element, we don't deal with constant. We want phi to be expressed as what? Phi equal to N1 V1 plus N2 V1 plus N3 V2 plus N4 what? V2. So how do we get this? How do we get that? Can you tell me? How do we get that? We need to use boundary condition. We know that the deflection at x equal to 0 is equal to V1. Put x equal to 0 here. What do you get? You get A4. Okay. We know that the slope at x equal to 0, which is the left node, equal to V1. We get A3. A3 equal to V1. You know from here you can solve for A1, A2, A3. Then what A4? Then what do? You go back and substitute in the function. Right? And when you substitute in the function, what will happen? When you substitute in the function, A1, A2, A4. Yeah. Then you substitute in this function, V equal to what? Can you tell me? Is it A1 plus A2, let's say x squared plus A3 x cubed, right?
Yeah.
Plus A4x, let's say something like that. And then you evaluate this. You know A1, you know A2, you know A3, you know A4. What do you do with this A's?
Apply the boundary.
No, I'm asking him. No, we are applying boundary condition here. We are applying boundary condition to get the constant. A1, A2, A3, A4. What do you do next? I'm giving you a hint. I'm giving you a hint here. I'm giving you already a hint here. I don't like form A1, A2, A3, A4. I like N1, N2, N3, N4. I like N1 times what? V1 plus N2 times V1. How do you do it? Very easy. You take the A's and put them back into the function. Where is the A? It's not here. Where? It's here. Okay, here. Look. We put A1, A2. Is this good form?
No.
This is not good form. It's true, you substitute A1, A2, A3, but this is not good. Now, how do you make it in this form? N1, V1 plus N2, V1 plus this. You gather the term. Can you tell me what is N1 from here? Anything that is multiplied by V1 is called part of N1. Can you tell me what would be N1? N1 equal. What? 2 over L cubed times X cubed, right? 2 X cubed over? That's it? No, enough. I want to see it. Yes, it's here. 2 X cubed. That's it. You just gather the term. Anything that's multiplied by V1 is called N1. Anything multiplied by V2 is called? Anything multiplied by V2 is called what? N3, right? Anything multiplied by V2? Yeah. Correct. Okay. So that's it. N1, N2, N3, N4. What is the property of N1, N2, N3, and 4? N1 equal to 1 at node 1. And N1 equal to 0 where? At node 2? Where? We have only 2 nodes. Remember, we have node 1 and node 2. We don't have 3 nodes, right? We don't have 4 nodes. We have 4 degrees of freedom, but we have only 2 nodes. So evaluate this n. Evaluate n. Shabab, evaluate n1 at x equal to 0. Do we get 1? 1. Okay, evaluate at x equal to L. 0. Okay, let's go to N2. Evaluate N2 at node 1. Do we get 1 or 0?
0.
We get 0.
1.
I don't know. Just put it.
1. 0. That's fine.
Put here 0.
0.
0. 0. So how come N2 is 0? How come? How come N2 is 0?
It is a fixed support, there is no rotation.
Huh?
There is no rotation.
We talk about primary and node. Your primary and node is only V1 and V2. So your primary function is N1 and N3. This one is multiplied by V1 and this one is multiplied by what? By V2. Okay. Anyway, next step is what? Relationship between stress and strain. Why do you want to find relationship between stress and strain? So that we can calculate the stresses. And then after the stresses, we can what? We can calculate the moment, right? Sigma equal to my over I. Once you know sigma, you see, this is how you look at the whole picture. You start with primary unknown, which is what? V. And at the end, you want to calculate all the other things. So this is the strain. And now, by the way, strain is equal to stretch. But U is not a primary unknown. This is secondary unknown. So you have to relate the displacement to vertical. You have to relate the stretch to the vertical displacement. That's why you see U is function of the rotation. You see, this is your primary unknown. V is secondary unknown. U is secondary unknown. This is how. It's mechanics here, okay? So this is U. What do you do with this U here? After you find U, you see it's from here. Look, this is the relationship between the displacement. This one here is the rotation, and this distance. And then you find, look, we substitute here this one, and then the stress. And then from the stress, we can find the moment. Do you have this formula before? Do we know it before? Do we know this before? That's it. If we know V, we can calculate the moment and we can calculate the shear. Huh? Sorry? لو ترفع صوتك شوي. بس في النهاية what stress is a secondary. Once you calculate the moment, you can put it here and calculate the stress. Because at the end you want to calculate stress, yes. You see, you want to find the moment and then you can calculate the stress. Very good. Derive element stiffness. Yalla, mashallah, this is your task. How do you calculate the stiffness from the direct stiffness method? Okay, let's start with this. Do you agree on this? That the force is equal to the shear at node 1. The moment will be equal minus M. At node 2, the force will be equal minus V. And at node 2, the moment equal the moment. Did you know how did I get this? Comparing the two figures. If it is in the same direction, I will say plus. If it is opposite, I will say minus. Okay. Now, how do you go from the shear to the deflection? We have a formula that the shear equal EI third derivative. What is the moment? EI second derivative. And you put the minus sign, okay? Now, how do we do it? Okay, how do we do it? Only I want the first one. Only I want the first one. Can you tell me? Okay. Only the first one. Go to the basic V, right?
Yeah,
what is V? V equal to, yalla, V equal to what? N1. You know it. V equal to N1 U1 plus N2 U2 plus N3, right? This is, no, this is V1 N3 V, not U, because this is the vertical displacement. Okay, then plus N4 V2. Okay. Now you need the second derivative or the third? Third, no problem. Let's do the third derivative. Okay, the third derivative of V dx cubed equal to, it's the third derivative of N1 V1 plus the third derivative of N2 V2 plus the third derivative of N3, right? V2 plus the third derivative of N4, right? Times V2. Okay, can you tell me what is the third derivative of N1 with N, the third derivative of N1? Can you tell me from here? Can you tell me the result from here? Just watch. What is the third derivative of N1 with x cubed? 12. EI divided by L cubed. Right? Anything that's multiplied by V1, anything that's multiplied by V1 is this. Okay, you know the third derivative of N2? It's there. Now what do you do after that? Okay, the left-hand side you have F1, M1, F2, M2. Now you need to pull out what? V1, V1, V2, V2. Anything that is left will be the stiffness. Oh, it's here. Yes, 12. EI divided by L cubed. So this is the stiffness. That is the stiffness. Time up, right? Yeah, I saw your eyes, don't worry. I saw. Your eyes start to close, right? That's it. This is what? Stiffness method for beams, right? Using what? Direct method, right? Direct method. Oh, I wish that I can finish more than that. Are you happy with me? We didn't do the third presentation. Okay. No problem. It's okay. We'll cover it next class. Okay. So shall I say stop sharing? First, stop sharing. Stop recording first. Again, always you go to more.